What is light? Fall asleep with the universe's quietest secret. Before every question you have ever asked, before every answer you have ever received, there was light. It fills your eyes when you open them in the morning. It dances on water, filters through leaves, illuminates the pages of books, and carries images from distant stars across unimaginable distances to reach you. Light is everywhere, yet it remains one of the universe's most profound mysteries, a secret so quiet that it whispers in every moment, in every photon that touches your skin, in every wavelength that your eyes cannot see but that nevertheless shapes the reality around you. This is not a story about light as a mere physical phenomenon, though it is that. It is an invitation to contemplate something so fundamental to existence that without it, the universe would be not just dark, but fundamentally different. Light is not simply illumination, it is information, energy, time, and space woven together in a form that travels at the ultimate speed, carrying with it the history of everything it has touched. As you prepare to rest, consider this: every photon that reaches you has traveled. Some have journeyed for billions of years, carrying messages from the early universe. Others were created moments ago, reflected from nearby surfaces. All of them move at the same speed, the cosmic speed limit 299,792,458 meters per second, a number so precise and so universal that it defines not just how fast light travels, but how space and time themselves are structured. Light is the universe's quietest secret because it is so ordinary that we take it for granted, yet so extraordinary that it challenges our deepest understanding of reality. It behaves as both particle and wave, exists in a state of quantum uncertainty, and carries information about events that occurred long before you were born. In its gentle presence, the cosmos reveals itself, layer by layer, moment by moment. Tonight, as you drift towards sleep, let light be your guide. Not the harsh glare of screens or the artificial brightness of lamps, but the deeper understanding of what light truly is: a fundamental force of nature, a messenger from the past, a creator of reality, and a bridge between the quantum world and the cosmos at large. In contemplating light, you touch something eternal, something that connects you to the very fabric of space-time itself. The question, what is light, has been asked for thousands of years, and each generation has found new layers to the answer. Ancient philosophers saw light as a divine essence, a connection to the heavens, a symbol of knowledge and truth. Plato described vision as light emanating from the eyes, while Aristotle proposed that light was a quality of transparent media. These early theories, though incorrect in their details, recognized that light was something fundamental, something that connected the observer to the observed. The Islamic Golden Age brought remarkable advances in understanding light. Ibn al-Haytham, working in the 11th century, conducted systematic experiments with light, using dark rooms with small apertures to study how light travels. He correctly proposed that light travels in straight lines and that vision occurs when light enters the eye, not when it emanates from it. His work on reflection and refraction laid the foundation for the scientific study of optics and demonstrated the power of experimental method. The Renaissance saw further advances, with artists studying light and shadow to create more realistic paintings. Leonardo da Vinci made detailed observations of light's behavior, noting how it reflects, refracts, and creates shadows. The camera obscura, a device that projects an image through a small hole, was used both as an artistic tool and as a way to study light's properties. These practical applications drove deeper understanding of how light behaves. Newton's experiments with prisms in the 17th century revealed that white light contains all colors, dispelling the ancient belief that colors were modifications of white light. His corpuscular theory, describing light as streams of particles, explained reflection and some aspects of refraction. But it struggled with phenomena like interference and diffraction, which seemed to require a wave description. The debate between particle and wave theories would persist for over a century. Huygens proposed a wave theory of light, suggesting that light propagates as waves through an ether, a hypothetical medium filling space. This theory could explain interference and diffraction, phenomena where light seems to bend around obstacles and create patterns of light and dark. But the wave theory had its own problems, particularly in explaining why light travels in straight lines and how it could travel through the vacuum of space if it required the medium. Maxwell's unification of electricity and magnetism in the 19th century provided the theoretical framework that resolved many of these questions. His equation showed that light is an electromagnetic wave, a self-propagating oscillation of electric and magnetic fields. The speed of light appeared naturally in these equations, and Maxwell correctly predicted that light, electricity, and magnetism are all manifestations of the same fundamental force. This unification was one of the greatest achievements in physics, revealing deep connections between phenomena that had seemed separate. Einstein's work in the early 20th century transformed our understanding yet again. His explanation of the photoelectric effect required treating light as particles, photons, with energy proportional to frequency. This particle description, combined with the wave description from Maxwell's equations, created the wave-particle duality that is central to quantum mechanics. His theory of special relativity showed that the speed of light is a fundamental constant, the same for all observers, leading to remarkable consequences like time dilation and length contraction. Modern physics reveals light as something far more complex, a quantum field excitation that exhibits properties of both particles and waves, that has no mass yet carries energy and momentum, that travels through the vacuum of space yet requires no medium. Quantum field theory describes light as excitations of the electromagnetic field, where photons are quantized vibrations of this field. This description unifies the wave and particle aspects, showing that they are complementary views of the same underlying reality. To understand light is to understand something about the universe itself. Light is electromagnetic radiation, a self-propagating wave of electric and magnetic fields oscillating perpendicular to each other and to the direction of travel. This elegant description, captured in Maxwell's equations, unified electricity, magnetism, and optics into a single framework. But it was only the beginning of the story. Light exists across an enormous spectrum. The narrow band that human eyes can perceive, from violet at around 400 nanometers to red at 700 nanometers, represents only a tiny fraction of the electromagnetic spectrum. Beyond visible light, there are radio waves with wavelengths measured in meters or kilometers, microwaves, infrared radiation that we feel as heat, ultraviolet light that causes sunburns, X-rays that reveal the structure of bones, and gamma rays with wavelengths smaller than atomic nuclei. All of these are light, differing only in frequency and wavelength. A radio wave and a gamma ray are fundamentally the same phenomenon, separated by a factor of trillions in their energy and frequency. This unity across scales is one of light's remarkable properties. The same physics governs the gentle warmth of infrared radiation and the destructive power of gamma rays. At the quantum level, light reveals its particle nature. Photons, the quantum of electromagnetic radiation, are massless particles that always travel at the speed of light. They carry energy proportional to their frequency, as described by the relationship E equals h times nu, where h is Planck's constant and nu is the frequency. This simple equation connects the wave and particle aspects of light, showing that higher frequency light carries more energy per photon. The wave-particle duality of light is not a contradiction, but a deeper truth about reality. Light behaves as a wave when it passes through slits and creates interference patterns, spreading out and overlapping with itself. It behaves as a particle when it strikes a detector and deposits its energy at a specific point. Both descriptions are necessary and complementary, revealing that our classical intuitions about waves and particles are approximations of a more fundamental quantum reality. Light's interaction with matter is equally profound. When light encounters an atom, it can be absorbed, raising an electron to a higher energy level. When that electron falls back, it emits light, often at a specific wavelength characteristic of that element. This is how astronomers determine the composition of distant stars, by analyzing the spectrum of light they emit, looking for the dark absorption lines or bright emission lines that reveal the presence of specific elements. The speed of light, c, is not just a number but a fundamental constant of nature. Its value, 299,792,458 meters per second, is so precisely known that the meter is now defined in terms of it. This constancy appears in Einstein's famous equation E equals mc squared, showing the equivalence of mass and energy. It defines the geometry of spacetime in general relativity, when nothing can travel faster than light, and where light itself follows the curved path created by massive objects. The speed of light is the same for all observers, regardless of their motion, a fact that leads to the strange and beautiful consequences of special relativity. Time dilation means that moving clocks run slow relative to stationary ones. Length contraction means that moving objects appear shortened in their direction of motion. The relativity of simultaneity means that events simultaneous for one observer may not be for another. These effects, though counterintuitive, have been verified in countless experiments and are essential for technologies like GPS, which must account for relativistic effects to function accurately. The constancy of the speed of light has profound implications for causality. Since nothing can travel faster than light, there is a maximum speed at which information or influence can propagate. This creates light cones and spacetime diagrams, regions that define what events can influence or be influenced by a given point. Events outside each other's light cones cannot have any causal connection, preserving the logical structure of cause and effect even in a relativistic universe. In general relativity, light's path is determined by the curvature of spacetime. Massive objects warp spacetime, and light follows the straightest possible paths in this curved geometry, called geodesics. This means that light doesn't just travel in straight lines, but follows curved paths around massive objects. The bending of starlight by the sun, observed during solar eclipses, provided early confirmation of general relativity and showed that light is intimately connected to the structure of space-time itself. The speed of light also appears in the relationship between electric and magnetic fields. In Maxwell's equations, the speed of light emerges from the fundamental constants that describe electricity and magnetism. This connection suggests that light is not separate from these forces but is their natural manifestation. The fact that light's speed is finite, not infinite, means that electromagnetic effects propagate at a finite rate, creating the possibility of electromagnetic waves that can travel independently of their source. The quantum mechanical description of light reveals that photons always travel at the speed of light in vacuum, never slower and never faster. Unlike massive particles, which can be accelerated or decelerated, photons are born moving at light speed and continue at that speed until they are absorbed. This constancy is a fundamental property of massless particles and reflects the deep structure of spacetime and quantum field theory. Light is energy in motion, and that energy can be harnessed, transformed, and used. Solar panels convert light into electricity through the photoelectric effect, where photons knock electrons free from semiconductor materials, creating an electric current. The efficiency of solar cells has improved dramatically, with modern cells converting over 20% of incident light into electricity. Some experimental cells approach 50% efficiency, showing the potential for light to power human civilization. Plants use light in photosynthesis to create the chemical energy that sustains life on Earth. The process involves two main stages: light-dependent reactions, where photons are absorbed and their energy is used to create energy-carrying molecules, and light-independent reactions, where carbon dioxide is fixed into organic compounds. This process, powered by sunlight, produces the oxygen we breathe and the food we eat, making light the ultimate source of energy for almost all life. Lasers concentrate light into coherent beams that can cut through metal, perform delicate surgery, or carry information through fiber optic cables. The coherence of laser light, where all photons are in phase, allows it to be focused to extremely small spots and to maintain its intensity over long distances. This property has enabled countless applications, from barcode scanners to optical communication to scientific research. Light is not passive, it is an active force that shapes the world. Light pressure, though weak, can move objects and has been proposed for solar sails that could propel spacecraft using only sunlight. Light can trigger chemical reactions, drive phase transitions, and create excited states in matter. The interaction between light and matter is fundamental to chemistry, biology, and technology, making light one of the most versatile tools in science and engineering. Yet for all we understand about light, mysteries remain. Why does light have the speed it does? Why is it massless? What is the true nature of a photon? These questions probe the deepest levels of physics, touching on the nature of quantum fields, the structure of spacetime, and the fundamental laws that govern the universe. The history of understanding light is itself a journey to human knowledge. Ancient Greek philosophers debated whether vision worked by light emanating from the eyes or by light entering them. The Islamic Golden Age produced remarkable insights into optics, with scholars like Ibn al-Haytham conducting experiments that laid the foundation for the scientific method. Newton's experiments with prisms revealed that white light contains all colors, while his corpuscular theory described light as particles. Huygens proposed a wave theory, and the debate between particle and wave models persisted for centuries. Maxwell's unification of electricity and magnetism in the 19th century provided the theoretical framework that light is an electromagnetic wave. His equations predicted the speed of light and showed that light, electricity, and magnetism are all manifestations of the same fundamental force. This unification was one of the greatest achievements in physics, revealing deep connections between phenomena that had seemed separate. Einstein's work on the photoelectric effect and special relativity further transformed our understanding. The photoelectric effect required treating light as particles, photons, while special relativity showed that the speed of light is a fundamental constant of nature, the same for all observers. This constancy leads to remarkable consequences: time dilation, where moving clocks run slow; length contraction, where moving objects appear shortened; and the relativity of simultaneity, where events simultaneous for one observer may not be for another. Quantum mechanics added yet another layer, showing that light exhibits both wave and particle properties simultaneously. The uncertainty principle applies to light, meaning that certain pairs of properties cannot be known with perfect precision at the same time. Quantum field theory describes light as excitations of the electromagnetic field, connecting it to the deepest levels of physical reality. Modern applications of light span every aspect of technology and science. Fiber optic cables carry information as pulses of light, enabling the global internet. Lasers are used in everything from surgery to manufacturing to entertainment. Solar cells convert light into electricity, providing renewable energy. Light-based imaging techniques reveal structures from the atomic scale to the cosmic scale. Spectroscopy analyzes the composition of everything from distant stars to biological samples. Yet for all this understanding, fundamental questions remain. Why does light have exactly the speed it does? What is the true nature of a photon? How does light's wave-particle duality reflect deeper truths about reality? These questions connect to the most profound mysteries in physics, touching on the nature of space, time, matter, and the fundamental laws that govern the universe. As you contemplate light, remember that you are seeing it, feeling it, and being shaped by it in every moment. The screen you read from emits light. The room around you reflects and absorbs light. Your own body emits infrared radiation, a form of light invisible to your eyes but detectable by instruments. You are immersed in light, bathed in it, made possible by it. And as you prepare to close your eyes, know that light will continue its endless journey, carrying information across the cosmos, connecting you to stars and galaxies, to the past and the future, in ways that transcend ordinary understanding. Light is a time traveler. This is not metaphor, but literal truth. When you look at the stars, you are seeing them not as they are now, but as they were when the light left them. The nearest star beyond the Sun, Proxima Centauri, is about 4 light-years away, meaning the light reaching your eyes tonight began its journey 4 years ago. The light from the Andromeda Galaxy has been traveling for over 2 million years. When you gaze at the most distant galaxies visible through telescopes, you are looking billions of years into the past, seeing the universe as it was when it was young. This property of light, that it takes time to travel, transforms astronomy into a form of time travel. By looking farther away, astronomers look farther back in time. The most distant objects observable are also the oldest, the light having journeyed across most of cosmic history to reach us. In this way, light carries not just spatial information but temporal information, encoding the state of the universe at the moment it was emitted. The cosmic distance ladder, the series of methods astronomers use to measure distances across the universe, relies fundamentally on light. Parallax measurements use the apparent shift of nearby stars as Earth orbits the Sun. Cepheid variable stars pulse with the period related to their intrinsic brightness, allowing the distance to be determined from their apparent brightness. Type I supernovae have unknown peak brightness, making them standard candles for measuring vast distances. Each rung of this ladder depends on understanding how light propagates and how its properties relate to distance. The expansion of the universe adds another layer to light's journey. As space itself expands, light waves are stretched, their wavelengths lengthening and shifting toward the red end of the spectrum. This cosmological redshift means that light from distant galaxies arrives redder than when it was emitted. The amount of redshift directly relates to how far the light has travelled and how much the universe has expanded during that journey. In this way, light carries information not just about the objects that emitted it, but about the history of cosmic expansion itself. The cosmic microwave background radiation is perhaps the most dramatic example of light as a time traveler. This faint glow, discovered accidentally in 1965, fills the entire sky with microwaves corresponding to a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. This radiation is the oldest light in the universe, emitted when the cosmos was only about 380,000 years old, when atoms first formed and the universe became transparent. Before that moment, the universe was a hot, dense plasma of particles and radiation. Photons were constantly scattered by free electrons, unable to travel far. But as the universe expanded and cooled, electrons combined with nuclei to form neutral atoms. Suddenly, photons could travel freely. The light released at that moment has been streaming through space ever since, its its wavelength stretched by cosmic expansion from visible ultraviolet light into the microwave region. This ancient light carries a snapshot of the universe at a specific moment in its history. Tiny variations in its temperature fluctuations of 1 part in 100,000 reveal the seeds of cosmic structure. Slightly denser regions would later collapse under gravity to form galaxies and clusters. The pattern of these fluctuations, mapped in exquisite detail by satellites, provides a window into the early universe and tests theories about its origin and evolution. Light from more recent cosmic epochs tells other stories. The light from quasars, extremely bright objects powered by supermassive black holes, has traveled for billions of years. Along the way, it has passed through clouds of gas, each element absorbing light at specific wavelengths. These absorption lines create a forest of features in quasar spectra, revealing the composition and distribution of matter across cosmic time. By analyzing this light, astronomers can study how the universe evolved, how elements were created and distributed, and how structures formed. The light from supernova, the explosive deaths of massive stars, serves as both distance markers and element factories. These events are so bright that they can outshine entire galaxies, making them visible across vast distances. Their light reveals the processes of nuclear synthesis, showing how heavy elements are forged in stellar explosions. The light curves of Type I supernova, with a consistent peak brightness, have been crucial in discovering that the expansion of the universe is accelerating, driven by the mysterious dark energy. Even the light from our own sun tells the story of time. The photons that warm your skin were created in the sun's core, where nuclear fusion converts hydrogen into helium. But these photons did not travel directly to the surface. Instead, they underwent a random walk, being absorbed and re-emitted countless times over tens of thousands of years. The light you see from the sun was created long before human civilization began, finally escaping the solar surface about 8 minutes ago to reach Earth. Light's role as a time traveler extends to the quantum realm as well. In quantum field theory, particles can be created and annihilated, and virtual particles constantly pop in and out of existence. The electromagnetic field itself is a quantum field, and photons are its excitations. This means that light, at the most fundamental level, is connected to the quantum vacuum, to the fluctuations that occur even in empty space. The relationship between light and time goes deeper than travel time. In special relativity, the speed of light defines the structure of spacetime. Events that are simultaneous for one observer may not be simultaneous for another moving observer. The faster you move, the more time dilates and lengths contract, all relative to the speed of light. Light itself experiences no time from a photon's perspective. If such a perspective has meaning, its entire journey from emission to absorption occurs in zero time, regardless of the distance traveled. This connection between light and time suggests that understanding light is essential to understanding time itself. Light is not just a traveler through time, it is part of the fabric that defines temporal relationships. The constancy of the speed of light for all observers is what makes the universe's causal structure consistent, ensuring that cause and effect maintain their proper order. The concept of look-back time, the time it takes light to travel from a source to an observer, transforms our understanding of cosmic history. When astronomers observe a galaxy at a redshift of 1, they are seeing it as it was when the universe was half its current age. At higher redshifts, they probe even earlier epochs. The most distant galaxies observed have redshifts greater than 10, meaning their light has travelled for over 13 billion years, showing the universe when it was less than a billion years old. This temporal layering means that different observations probe different cosmic epochs simultaneously. The cosmic microwave background shows the universe at 380,000 years. Quasars reveal the universe at billions of years. Nearby stars show relatively recent cosmic history. All of these different times are present in the light reaching Earth right now, creating a kind of temporal collage of cosmic evolution. The finite speed of light also creates observable horizons. The particle horizon marks the maximum distance from which light could have reached us since the Big Bang. The event horizon marks the maximum distance from which light will ever be able to reach us in the future, given the universe's accelerating expansion. These horizons define the limits of what can be observed, creating boundaries in both space and time. Light's role as a time traveler is not just passive observation but active archaeology. By analyzing the spectrum, intensity, and polarization of light from different epochs, astronomers can reconstruct the universe's history. They can trace how galaxies formed and evolved, how elements were created and distributed, how the expansion rate changed over time. Light carries this historical information encoded in its properties, waiting to be decoded by careful observation and analysis. The time dilation effects of special and general relativity add further complexity to light's temporal journey. Light from distant, rapidly moving objects is time dilated, meaning events appear to unfold more slowly. Light passing through strong gravitational fields experiences gravitational time dilation, with clocks running slower in regions of stronger gravity. These effects, though small in most cases, become significant for objects near black holes or moving at relativistic speeds. As you consider light's journey through time, remember that the photons reaching you now connect you to events across cosmic history. The starlight in your eyes links you to processes that occurred long before Earth formed. The cosmic microwave background connects you to the universe's infancy. Even the light from nearby objects, though recent, has still traveled, still taken time to reach you. In this way, everything you see is slightly in the past, and light is the messenger that bridges those temporal gaps. The present moment, as you experience it, is actually a collection of light from many different times, all arriving simultaneously, creating a rich tapestry of cosmic history in every glance. The story of light begins with the story of the universe itself. In the first moments after the Big Bang, the cosmos was a seething cauldron of energy, too hot and dense for atoms to exist. Matter and radiation were tightly coupled, with photons constantly scattering off free electrons and other charged particles. Light existed, but it could not travel freely. The universe was opaque, a brilliant fireball where radiation and matter were in thermal equilibrium. As the universe expanded, it cooled. About 1 second after the Big Bang, the temperature had dropped enough for protons and neutrons to form from quarks. A few minutes later, during a period called Big Bang nucleosynthesis, light atomic nuclei began to form deuterium, helium, and traces of lithium. But electrons remained free and the universe remained opaque to light. This state persisted for hundreds of thousands of years. The universe continued expanding and cooling, but photons were still trapped, unable to travel far without scattering. Density fluctuations, tiny variations in the distribution of matter, began to grow under the influence of gravity, but their effects were largely hidden in the opaque plasma. Then, around 380,000 years after the Big Bang, something remarkable happened. The temperature dropped to about 3000 Kelvin, low enough for electrons to bind with nuclei and form stable, neutral atoms. This process, called recombination, fundamentally changed the universe's relationship with light. With most electrons now bound in atoms, photons could travel much farther before scattering. The universe transitioned from opaque to transparent in a cosmic instant. The light released at that moment is what we now observe as the cosmic microwave background. Initially, this light would have been visible with wavelengths in the optical or near-infrared range. But as the universe continued expanding over the next 13.8 billion years, those wavelengths were stretched by a factor of about 1100, shifting them into the microwave region of the spectrum. What was once visible light is now detected as microwaves with a temperature equivalent of 2.7 Kelvin. This ancient light is not uniform. Embedded within it are tiny temperature fluctuations, variations of about 1 part in 100,000. These fluctuations are not random noise but contain crucial information about the early universe. They represent regions where the density was slightly higher or lower than average, where the temperature was slightly warmer or cooler. These small variations would become the seeds of cosmic structure. The pattern of these fluctuations has been mapped in extraordinary detail by satellites like COBE, WMAP, and Planck. The angular power spectrum, how the size of fluctuations varies with angular scale on the sky, reveals the acoustic oscillations that were frozen in when the universe became transparent. Before recombination, gravity tried to compress slightly over dense regions, while radiation pressure pushed back. This created sound waves in the plasma, oscillations that were caught at different phases when recombination occurred. The positions and amplitudes of the peaks in this power spectrum encode fundamental information about the universe, its geometry, its composition, its age, and the nature of the initial fluctuations. The fact that the spectrum matches predictions so well provides strong evidence for the Big Bang model and for cosmic inflation, the theory that the universe underwent a period of extremely rapid expansion in its first fraction of a second. The cosmic microwave background is often called a baby picture of the universe, and the metaphor is apt. Just as a baby picture captures a moment in time, frozen and preserved, the microwave background captures the universe at a specific cosmic age. But unlike a static photograph, This image is dynamic. It continues to reach us from all directions, a constant reminder of the universe's origin. Light's role in revealing cosmic origins extends beyond the microwave background. The first stars and galaxies formed hundreds of millions of years after recombination during what astronomers call the cosmic dark ages. These first luminous objects began the process of reionization, the ultraviolet radiation stripping electrons from neutral hydrogen atoms and making the intergalactic medium transparent again to certain wavelengths of light. The light from these first stars and galaxies, heavily redshifted by cosmic expansion, is extremely faint and difficult to detect. But it carries information about the universe's transition from darkness to light, from simplicity to complexity. Future telescopes hope to detect this first light to see the universe as it was when stars first began to shine. Light also reveals the universe's composition. The spectrum of light from distant objects shows absorption and emission lines that reveal the presence of specific elements. The relative abundances of these elements match predictions from Big Bang nucleosynthesis and stellar evolution, confirming our understanding of how the universe's chemical composition developed over time. The way light interacts with matter provides clues about the universe's structure. Gravitational lensing, where massive objects bend light's path, reveals the distribution of dark matter, the mysterious substance that makes up most of the universe's mass. Dark matter doesn't emit or absorb light, making it invisible to direct observation, but its gravitational effects bend light's path, creating detectable distortions. By mapping these distortions across the sky, astronomers can create three-dimensional maps of dark matter distribution, revealing the cosmic web of structure that would otherwise be invisible. The way light is redshifted by cosmic expansion provides evidence for dark energy, the even more mysterious force causing that expansion to accelerate. Observations of distant supernovae showed that the universe's expansion is accelerating, not slowing down as expected. This acceleration requires a repulsive force, called dark energy, that counteracts gravity on cosmic scales. The nature of dark energy remains one of the greatest mysteries in physics, but its effects are encoded in the light from distant objects, waiting to be decoded by careful observation. The polarization of light also carries information about the universe's structure. The cosmic microwave background is polarized due to scattering in the early universe, and this polarization pattern encodes information about the universe's geometry, composition, and the nature of the initial fluctuations. The search for B-mode polarization, which could reveal primordial gravitational waves from cosmic inflation, is one of the most active areas in cosmology, potentially providing direct evidence for physics at energies far beyond what can be achieved in particle accelerators. In all these ways, light serves as a cosmic archaeologist tool, revealing layers of history encoded in its properties. The wavelength, the spectrum, the polarization, the intensity all carry information about the source that emitted the light and the journey it has taken. By carefully analyzing this information, astronomers can reconstruct the universe's history from its hot, dense beginning to its current state of complex structure. The cosmic microwave background, in particular, encodes the initial conditions of the universe. The pattern of fluctuations it contains was imprinted by processes that occurred even earlier, possibly during cosmic inflation. These quantum fluctuations, stretched to cosmic scales by rapid expansion, became the seeds of all structure. Without them, the universe would be perfectly uniform, with no galaxies, no stars, no planets, and no observers to wonder about light's origins. The process of recombination was not instantaneous, but occurred over thousands of years as the universe cooled. During this transition, the probability of an electron being bound to a nucleus gradually increased. The last scattering surface, the moment when most photons last interacted with matter, is not a sharp boundary but a fuzzy epoch. This fuzziness has observable consequences, slightly blurring the features in the cosmic microwave background and providing information about the recombination process itself. The acoustic oscillations frozen into the microwave background are like cosmic sound waves, ripples in the primordial plasma. Before recombination, gravity tried to compress slightly over dense regions, while radiation pressure pushed back, creating oscillations. The fundamental mode, the largest scale oscillation, has a characteristic size determined by the speed of sound in the plasma and the age of the universe at recombination. This size, about 300,000 light-years at that time, now appears as an angular scale of about 1 degree on the sky due to cosmic expansion. Higher harmonic modes create additional peaks in the power spectrum, each providing information about the universe's composition and geometry. The relative heights of these peaks reveal the relative contributions of matter, radiation, and dark energy. The positions of the peaks depend on the universe's curvature, with a flat universe producing peaks at specific angular scales. The detailed agreement between observations and theoretical predictions provides strong evidence for the Big Bang model and for specific values of cosmological parameters. The polarization of the cosmic microwave background carries additional information. E-mode polarization, created by density fluctuations, provides a complementary view of the early universe. B-mode polarization, if detected, could reveal primordial gravitational waves from cosmic inflation, providing direct evidence for the universe's exponential expansion in its first fraction of a second. The search for these B-modes is one of the most active areas in cosmology, potentially revealing physics at energies far beyond what can be achieved in particle accelerators. The cosmic microwave background is not perfectly uniform, but contains tiny temperature fluctuations of about 1 part in 100,000. These fluctuations are not random, but follow a specific statistical pattern, nearly Gaussian and nearly scale invariant, as predicted by inflationary cosmology. The slight deviation from perfect scale invariance, called the spectral tilt, provides information about this specific model of inflation and the physics of the very early universe. As you contemplate light's connection to the birth of the universe, remember that the photons reaching you from the cosmic microwave background are among the oldest things you can directly observe. They have traveled for nearly 14 billion years, carrying a message from the universe's infancy. In their gentle, uniform presence, filling every direction you look, you are connected to the moment when light first became free, when the universe first became transparent, when the cosmic story of structure and complexity truly began. These ancient photons, cooled and redshifted by cosmic expansion, are a direct link to the universe's origin, a whisper from the cosmos's first breath of light. Light does not merely illuminate reality in a profound sense, it creates it. This is not to say that light brings objects into existence from nothing, but rather that our perception of reality, our understanding of the world, and even the way matter behaves are all fundamentally shaped by light and its interactions. Consider vision, the most direct way light creates your experience of reality. When light reflects off an object and enters your eye, it carries information about the object's properties, its color, its texture, its shape, its distance. Your brain processes this information, constructing a three-dimensional model of the world around you. But this model is not the world itself, it is a representation built from light. Without light, there would be no vision, and your experience of reality would be fundamentally different. The colors you see are not inherent properties of objects, but arise from the interaction between light and matter. An apple appears red not because it is red in some absolute sense, but because its surface absorbs most wavelengths of light and reflects primarily red wavelengths. The light itself has no color. Color is created in your brain's interpretation of different wavelengths. What you perceive as red light is electromagnetic radiation with a wavelength around 650 nanometers, but the experience of redness is a construction of your nervous system. This relationship between light and perception extends beyond vision. Many animals can see wavelengths invisible to humans. Bees see ultraviolet light, which helps them locate nectar guides on flowers. Some snakes can detect infrared radiation, allowing them to sense the body heat of prey. Each species experiences a different reality, filtered through the wavelengths of light their eyes can detect. Light's role in creating reality goes deeper than perception. Through the process of photosynthesis, light literally creates the chemical energy that sustains life on Earth. Plants capture photons and use their energy to convert carbon dioxide and water into glucose and oxygen. This process, powered by sunlight, forms the base of almost all food chains. The energy stored in the food you eat, the oxygen you breathe, and the fossil fuels that power civilization all trace back to light captured by plants and algae. The way light interacts with matter determines the properties of materials. When light strikes a surface, it can be reflected, absorbed, or transmitted. These interactions depend on the material's atomic structure, its electronic configuration, and the wavelength of the light. A mirror reflects light because its surface is smooth and its electrons can oscillate in response to the incoming electromagnetic wave. A black surface absorbs light because its structure converts the light's energy into heat. A transparent material like glass transmits light because its atoms are arranged in a way that allows photons to pass through with minimal interaction. Light pressure, though extremely weak, is a real force that can influence matter. When light reflects off a surface, it transfers momentum, exerting a tiny push. This radiation pressure is what allows solar sails to work, using sunlight to propel spacecraft. On cosmic scales, light pressure from stars can help prevent gravitational collapse in some stellar environments and can drive stellar winds that eject material into space. The quantum nature of light creates reality in even more fundamental ways. When a photon is absorbed by an atom, it can raise an electron to a higher energy level. This change in the atom's state is real and measurable. The atom is different after absorbing the photon. In this sense, light doesn't just reveal reality, it actively modifies it. The act of observation in quantum mechanics, where measuring a system necessarily disturbs it, is fundamentally connected to light and other forms of electromagnetic interaction. Light carries information, and information is a form of reality. The light from a distant star carries information about that star's temperature, composition, motion, and age. When that light reaches a telescope and is analyzed, that information becomes part of human knowledge, part of our understanding of reality. In this way, light bridges a gap between distant objects and local observation, making the remote accessible in the past-present. The coherence of light, as in lasers, creates possibilities that incoherent light cannot. Laser light, with its waves all in phase, can be focused to extremely small spots, cut through materials, carry information through fiber optic cables, and create holograms that record three-dimensional information. The properties of coherent light have enabled technologies that shape modern life, from barcode scanners to optical communication networks to medical procedures. Light's interaction with the quantum vacuum reveals another layer of reality creation. According to quantum field theory, empty space is not truly empty, but filled with virtual particles constantly appearing and disappearing. These fluctuations can affect light, causing effects like the Casimir force and contributing to the Lamb shift in atomic spectra. Even in the absence of matter, light is connected to the underlying quantum structure of space itself. The way light behaves in different media creates optical phenomena that seem to bend reality. Refraction, where light changes direction when entering a new medium, makes objects appear in different positions than they actually occupy. A straw in a glass of water appears bent because light from the submerged portion refracts at the water's surface. Mirages occur when light bends due to temperature gradients in the air, creating images of objects that aren't where they appear to be. Light's role in creating reality extends to the cosmic scale. The light from stars and galaxies is what makes them visible, what allows astronomers to study them. Without light, these objects would exist but would be undetectable, effectively outside our reality. The cosmic microwave background, by making the early universe observable, brings the epoch into our scientific reality, allowing us to study and understand it. The way light creates color perception reveals the constructed nature of reality. Human vision relies on 3 types of cone cells, each sensitive to different ranges of wavelengths. The brain combines signals from these cells to create the experience of color, but this means that different combinations of wavelengths can produce the same color experience, a phenomenon called metamerism. The color you perceive is not a direct property of the light, but a construction of your visual system. This construction extends to other aspects of vision. Depth perception relies on multiple cues: binocular disparity, motion parallax, perspective, and shading. The brain integrates these cues to create a 3-dimensional model of the world. But this model is an interpretation, not a direct copy. Optical illusions reveal the ways in which this interpretation can be fooled, showing that perception is an active process of construction rather than passive reception. Light's role in creating biological reality extends far beyond vision. Photosynthesis, the process by which plants convert light energy into chemical energy, is the foundation of almost all life on Earth. The chlorophyll molecule absorbs photons, using that energy to drive chemical reactions that produce glucose from carbon dioxide and water. This process, powered by sunlight, creates the energy that flows through ecosystems, from plants to herbivores to carnivores, ultimately supporting all life. The efficiency of photosynthesis is remarkable. Plants can convert about 5% of the light energy they receive into chemical energy, a process that has been refined over billions of years of evolution. The specific wavelengths absorbed by chlorophyll, primarily in the blue and red regions of the spectrum, are those that carry the most energy per photon in the visible range. Green light, which chlorophyll reflects rather than absorbs, is why plants appear green. Light also creates reality through its effects on materials. The way light interacts with matter determines not just how things appear but how they behave. Semiconductors, the foundation of modern electronics, work by absorbing photons to create electron-hole pairs. Solar cells use the photoelectric effect to convert light into electricity. Photocatalysts use light to drive chemical reactions. In all these cases, light doesn't just reveal reality, it actively creates new states and processes. The quantum mechanical description of light-matter interaction reveals even deeper connections. When a photon is absorbed, it doesn't just transfer energy, it changes the quantum state of the absorbing system. This change can trigger chemical reactions, create excited states, or drive phase transitions. The quantum nature of these interactions means that light doesn't just influence matter classically, but participates in quantum processes that shape reality at the most fundamental level. As you consider how light creates reality, remember that your entire experience of the world is mediated by light. The screen you read from, the room around you, the sky above all are made present to you through light. Even when you close your eyes, light continues to influence you, affecting your circadian rhythms, your mood, and your biological processes. Light is not separate from reality, it is woven into its very fabric, a fundamental thread in the tapestry of existence. Every color you see, every shape you perceive, every moment of visual experience is a creation of light, a collaboration between photons and your nervous system that constructs the reality you experience. The quantum nature of light reveals a world far stranger than everyday experience suggests. At the smallest scales, light behaves in ways that challenge classical intuition, showing that the universe operates according to rules that seem paradoxical but are nevertheless true. The photon, the quantum of light, is a massless particle that always travels at the speed of light. Unlike massive particles, photons cannot be at rest, they exist only in motion. This fundamental property connects to Einstein's theory of special relativity, where the speed of light is the same for all observers and represents the maximum speed at which information can travel. The energy of a photon is quantized, meaning it comes in discrete packets. A photon's energy is directly proportional to its frequency as given by E equals h nu, where h is Planck's constant. This quantization means that light cannot have arbitrary amounts of energy, it must come in specific, discrete amounts. When an atom emits or absorbs light, it does so by exchanging whole photons, never fractions of photons. This quantum nature becomes apparent in experiments like the photoelectric effect, where light shining on a metal surface ejects electrons. Classical wave theory predicted that the energy of ejected electrons should depend on the light's intensity, but experiments showed that it depends on the frequency instead. Only light above a certain frequency can eject electrons, regardless of intensity. This can only be explained by treating light as particles photons with energy proportional to frequency. The wave-particle duality of light is perhaps its most famous quantum property. In the double-slit experiment, light passing through two slits creates an interference pattern on a screen, characteristic of wave behavior. But if detectors are placed to determine which slit each photon passes through, the interference pattern disappears, and light behaves like particles. The act of measurement changes the behavior, suggesting that light exists in a superposition of states until observed. This leads to the uncertainty principle, which applies to light as well as matter. For a photon, there is a fundamental limit to how precisely both its position and momentum can be known simultaneously. The more precisely you know where a photon is, the less precisely you can know its momentum, and vice versa. This is not a limitation of measurement, but a fundamental property of quantum systems. Quantum entanglement, where particles become correlated in ways that cannot be explained by classical physics, also applies to light. Two photons can be created in an entangled state, where measuring a property of one instantly determines the corresponding property of the other, regardless of the distance between them. This spooky action at a distance, as Einstein called it, has been experimentally verified and is now used in quantum cryptography and quantum computing. The quantum field theory description of light treats it as excitations of the electromagnetic field. In this framework, the field itself is fundamental, and particles like photons are quantized vibrations of that field. The vacuum is not empty, but contains zero-point energy, fluctuations of the field that persist even at absolute zero temperature. These vacuum fluctuations have measurable effects, such as the spontaneous emission of light by excited atoms and the Casimir effect, where two parallel plates in a vacuum experience a small attractive force. Virtual photons, temporary fluctuations in the electromagnetic field, mediate the electromagnetic force between charged particles. When two electrons repel each other, they do so by exchanging virtual photons. These virtual particles exist only fleetingly, borrowing energy from the vacuum in accordance with the uncertainty principle, but their effects are real and measurable. The quantum nature of light becomes crucial in understanding atomic structure. When an electron in an atom makes a transition between energy levels, it emits or absorbs a photon with energy equal to the difference between those levels. The discrete nature of atomic energy levels, a consequence of quantum mechanics, means that atoms can only emit or absorb light at specific wavelengths, creating the characteristic spectral lines that identify each element. This quantization is why each element has a unique fingerprint in its spectrum, allowing astronomers to determine the composition of distant stars and galaxies simply by analyzing the light they emit. The precision of these spectral lines is so great that they can reveal not just what elements are present, but their temperature, density, motion, and even the presence of magnetic fields through the Zeeman effect, where spectral lines split in the presence of magnetic fields. Lasers exploit the quantum nature of light through stimulated emission. When an atom in an excited state is struck by a photon with energy matching the transition, it can be stimulated to emit another photon with the same energy, phase, and direction. This process, when applied to many atoms in a population inversion, creates a coherent beam of light where all photons are in phase and moving in the same direction. Quantum optics, the study of light at the quantum level, has revealed phenomena like photon antibunching, where photons are more likely to arrive separately than together, and quantum squeezing, where certain properties of light can be measured with precision beyond the classical limit. These effects have applications in precision measurement, quantum communication, and fundamental tests of physics. The relationship between light and quantum mechanics extends to the measurement problem, one of the deepest questions in physics. When does a quantum system collapse from a superposition of states to a definite state? The role of observation, often involving the detection of photons, raises questions about the nature of measurement and the boundary between quantum and classical behavior. Light's quantum nature also connects to information theory. A photon can carry quantum information, encoded in properties like polarization or orbital angular momentum. Quantum key distribution uses single photons to create unbreakable cryptographic keys, where any attempt to intercept the key would be detectable due to the quantum nature of the measurement process. As you contemplate the quantum nature of light, remember that these strange properties are not abstract concepts but real aspects of how light behaves. Every photon that reaches you is a quantum object, existing in a state of probability until it interacts with matter. The classical description of light as a wave or particle is an approximation that works well for many purposes but breaks down at the quantum level, where light reveals its true, more complex nature. The quantum world is not separate from the everyday world, it underlies it. The stability of matter, the behavior of chemical bonds, the emission of light by stars all depend on quantum mechanics. Light as a quantum phenomenon is a bridge between the microscopic quantum realm and the macroscopic world of experience, carrying quantum information across vast distances and making the quantum world accessible to observation. Quantum optics has revealed phenomena that seem to defy classical intuition. In quantum teleportation, the quantum state of a photon can be transferred to another photon at a distant location, even though the original photon is destroyed in the process. This doesn't involve faster-than-light communication, but relies on quantum entanglement, where two photons share a quantum state that cannot be described independently. The measurement of one photon instantly determines the state of the other regardless of distance, though no information is actually transmitted faster than light. Single photon sources and detectors have enabled experiments that probe the deepest aspects of quantum mechanics. The delayed choice quantum eraser experiment shows that the decision of whether to measure which path information can be made after a photon has already passed through an interferometer, yet it affects the interference pattern. This suggests that the photon's behavior is not determined until measurement, raising profound questions about the nature of reality and the role of observation. Quantum key distribution uses the quantum properties of light to create unbreakable cryptographic keys. Any attempt to intercept the key would disturb the quantum state, making the interception detectable. This application of quantum mechanics to practical security demonstrates that the strange properties of quantum light are not just theoretical curiosities but have real-world implications. The study of light at the quantum level has also revealed connections to other fundamental areas of physics. The Casimir effect, where two parallel plates in a vacuum experience an attractive force, arises from quantum fluctuations of the electromagnetic field. The Lamb shift, a small correction to atomic energy levels, comes from interactions with virtual photons in the quantum vacuum. These effects show that even empty space is not truly empty, but filled with quantum fluctuations that have measurable consequences. The relationship between light and quantum field theory extends to the concept of gauge symmetry, a fundamental principle in modern physics. The electromagnetic field is described by a gauge theory, where the physical predictions are independent of certain mathematical transformations. This gauge symmetry is not just a mathematical convenience, but reflects a deep property of nature, connecting light to the most fundamental structures of physical law. As you contemplate the quantum nature of light, consider that every photon that reaches you is a quantum object, existing in a state that transcends classical description. The wave-particle duality is not a limitation of our understanding, but a fundamental aspect of reality. Light's quantum nature connects it to the deepest levels of physical law, making it a window into the quantum world that underlies all of existence. Light is not a passive observer of the cosmos, but an active participant in its evolution. Through various mechanisms, light shapes the universe on scales from individual atoms to entire galaxies, influencing the formation of structure and the behavior of matter. Light pressure, though weak compared to other forces, has measurable effects. When photons strike a surface, they transfer momentum, creating a tiny force. This radiation pressure prevents some stars from collapsing under their own gravity. In massive stars, the outward pressure from light and other radiation balances the inward pull of gravity, maintaining stellar equilibrium. If this balance is disrupted, the star can expand or contract, sometimes explosively. The Eddington limit, named after the astrophysicist Arthur Eddington, describes the maximum luminosity a star can have while remaining stable. Beyond this limit, radiation pressure would exceed gravitational attraction, causing the outer layers of the star to be blown away. This limit helps explain why the most massive stars have finite lifetimes and why some stellar objects, like quasars, can be so luminous. Light pressure also drives stellar winds, streams of particles ejected from stars. In massive, hot stars, the intense radiation field accelerates material outward, creating winds that can carry away significant amounts of mass over the star's lifetime. These winds enrich the interstellar medium with heavy elements and can trigger star formation in nearby molecular clouds when they compress the gas. On smaller scales, light pressure from lasers can trap and manipulate individual atoms and particles. Optical tweezers use focused laser beams to hold microscopic objects in place, allowing scientists to study them without physical contact. This technique has applications in biology, chemistry, and physics, enabling precise manipulation of cells, molecules, and even individual atoms. Light's role in star formation is indirect but crucial. Stars form when dense regions in molecular clouds collapse under gravity. But this process is complex, involving the interplay of gravity, gas pressure, magnetic fields, and radiation. The light from newly formed stars, particularly massive ones, can heat surrounding gas, increasing pressure and potentially holding further star formation in that region. This feedback mechanism helps regulate the star formation rate in galaxies. In protoplanetary disks, the dusty disks around young stars where planets form, light plays multiple roles. Starlight heats the disk, creating temperature gradients that influence where different materials can condense. Light pressure can push small dust grains, affecting their distribution and potentially their growth into larger bodies. The way light scatters off dust grains makes these disks visible and allows astronomers to study their structure and composition. Light's interaction with cosmic dust shapes what astronomers can observe. Dust grains absorb and scatter light, particularly at shorter wavelengths, making some regions of space appear dark. But this same dust, when heated by starlight, emits infrared radiation, revealing structures that would otherwise be invisible. The study of infrared astronomy has opened new windows on star-forming regions, galactic centers, and the early universe. Gravitational lensing, where massive objects bend the path of light, is one of light's most dramatic cosmic interactions. Predicted by Einstein's general relativity, gravitational lensing occurs because massive objects warp spacetime, and light follows the curved paths created by this warping. The effect can magnify, distort, or multiply images of distant objects, creating cosmic mirages that reveal both the lensing object and the lens source. Strong gravitational lensing creates multiple images of a single source, sometimes forming arcs or even complete rings called Einstein rings. These effects allow astronomers to study objects that would otherwise be too faint to observe and to measure the mass of the lensing objects, including dark matter, which doesn't emit light but does bend its path. Weak gravitational lensing, a subtler effect where images are slightly distorted rather than multiplied, provides a way to map the distribution of dark matter across the universe. By analyzing the shapes of millions of distant galaxies, astronomers can detect the cumulative lensing effect of all matter along the line of sight, creating three-dimensional maps of cosmic structure. Microlensing, where a foreground object temporarily magnifies the light from a background star, has been used to detect exoplanets, brown dwarfs, and even isolated black holes. These events are rare and temporary, but they provide information about objects that are difficult to detect by other means. Light serves as a cosmic messenger, carrying information about distant objects across vast distances. The spectrum of light from a star reveals its temperature, composition, age, and motion. Absorption lines show what elements are present in the star's atmosphere and in any intervening material. Emission lines reveal hot, ionized gas. The overall shape of the spectrum indicates the star's temperature and evolutionary stage. The Doppler effect, where the wavelength of light changes due to motion, allows astronomers to measure velocities. Blue shift indicates motion toward the observer, redshift indicates motion away. This effect has been crucial in discovering exoplanets, where the slight motion of a star caused by an orbiting planet creates a periodic shift in spectral lines. It has also revealed the expansion of the universe, where distant galaxies show redshifts proportional to their distance. Light's polarization, the orientation of its electric field, carries additional information. Light scattered by dust grains becomes polarized, revealing the alignment of magnetic fields. Light from synchrotron radiation, emitted by electrons spiraling in magnetic fields, is also polarized, providing information about cosmic magnetic fields and high-energy processes. The time variability of light reveals dynamic processes. Pulsating stars change brightness in regular patterns, allowing astronomers to measure distances and study stellar interiors. Eclipsing binary stars show periodic dimming as one star passes in front of the other, revealing stellar masses, sizes, and orbital parameters. Supernova brighten and fade over days to weeks, their light curves encoding information about the explosion mechanism and the progenitor star. Light from different wavelengths reveals different aspects of cosmic objects. Radio waves show cold gas and magnetic fields. Infrared light reveals warm dust and cool stars. Visible light shows stellar surfaces and planetary atmospheres. Ultraviolet light reveals hot stars and ionized gas. X-rays reveal extremely hot gas and accretion processes. Gamma rays reveal the most energetic events in the universe. As you contemplate how light shapes the cosmos, remember that every photon carries information, and that information accumulates over time to build our understanding of the universe. The light reaching Earth from distant objects has traveled for millions or billions of years, carrying messages from the past. By carefully analyzing this light, astronomers can reconstruct cosmic history, understand physical processes, and explore the fundamental laws that govern the universe. Light is not separate from the cosmos, it is an integral part of it, both the product of cosmic processes and an influence on them. From the quantum interactions that create photons in stellar cores to the gravitational lensing that bends their paths, from the pressure that helps support stars to the information that reveals cosmic structure, light is woven into the fabric of cosmic evolution, a thread connecting the smallest quantum processes to the largest scales of the universe. The life cycle of light in the cosmos is a grand narrative spanning billions of years. Photons are created in stellar cores through nuclear fusion, where the energy released in converting hydrogen to helium emerges as gamma rays. These high-energy photons undergo a random walk through the star's interior, being absorbed and re-emitted countless times, gradually losing energy and shifting to longer wavelengths. After tens of thousands of years, they finally reach the stellar surface and escape into space. Once free, these photons travel through the interstellar medium, where they may be absorbed by gas clouds, scattered by dust grains, or redshifted by cosmic expansion. Some photons travel for billions of years before being absorbed by a planet, a telescope, or your eye. Others continue their journey indefinitely, carrying information about the source across cosmic distances. The interaction between light and cosmic dust creates some of the most beautiful phenomena in astronomy. Reflection nebulae, where starlight scatters off dust grains, create ethereal blue glows. Emission nebulae, where ultraviolet light from hot stars ionizes gas, produce vibrant colors as atoms recombine and emit light at specific wavelengths. Dark nebulae, dense clouds of dust that block background light, create silhouettes against brighter regions, revealing the three-dimensional structure of the interstellar medium. Light's role in cosmic feedback processes is crucial for understanding galaxy evolution. When massive stars swarm, their intense ultraviolet radiation can heat and ionize surrounding gas, creating HII region zones of ionized hydrogen. This heating increases pressure, potentially halting further star formation in that region. Supernova explosions, the deaths of massive stars, create shock waves that compress gas and trigger new star formation, while also enriching the interstellar medium with heavy elements. The cosmic web, the large-scale structure of the universe, is revealed through the light from galaxies distributed along filaments and nodes. The way light is registered by cosmic expansion allows astronomers to map this three-dimensional structure, revealing how matter is distributed across billions of light years. The pattern of this distribution, with its voids, filaments, and clusters, reflects the initial conditions of the universe and the processes that shaped cosmic evolution. Gravitational lensing, where massive objects bend light's path, has become one of the most powerful tools in cosmology. Strong lensing creates multiple images and dramatic arcs, allowing astronomers to study distant objects that would otherwise be too faint. Weak lensing, the subtle distortion of millions of galaxy shapes, maps the distribution of dark matter across the universe. Time delay measurements in lens quasars provide independent measurements of the expansion rate, helping to resolve current tensions in cosmology. The way light interacts with the intergalactic medium creates a forest of absorption lines and quasar spectra. As light from distant quasars passes through clouds of neutral hydrogen, specific wavelengths are absorbed, creating a Lyman alpha forest that reveals the distribution and properties of gas across cosmic time. This forest provides a three-dimensional map of the universe's matter distribution and tracks how the intergalactic medium evolved as galaxies formed and reionized the universe. As you contemplate how light shapes the cosmos, remember that every interaction, every absorption, every scattering carries information. The light reaching Earth has been shaped by everything it encountered on its journey, encoding a rich history of cosmic processes. By carefully analyzing this light, astronomers can reconstruct the universe's evolution, from its hot, dense beginning to its current state of complex structure, revealing the grand narrative of cosmic history written in photons. The relationship between light and consciousness is one of the most profound and mysterious connections in nature. Light enables vision, the primary way most humans experience the world, but the relationship goes deeper than simple perception. Light influences biological rhythms, affects mood and cognition, and raises fundamental questions about the nature of observation and reality. Vision begins when light enters the eye and strikes the retina, where specialized cells called photoreceptors convert light into electrical signals. Rod cells are sensitive to low light levels and provide black and white vision, while cone cells detect color and work best in brighter conditions. The process of phototransduction, where light energy triggers chemical changes that generate neural signals, is one of the most efficient processes in biology, able to detect single photons under optimal conditions. But vision is more than just detection. It involves complex processing in the brain. The raw signals from the retina are transformed through multiple layers of neural processing, extracting features like edges, motion, color, and depth. The brain constructs a coherent representation of the world from these signals, filling in gaps, interpreting ambiguous information, and creating the experience of seeing. This construction means that what you see is not a direct copy of reality but an interpretation, a model built by your brain from limited information. Optical illusions reveal the ways in which this construction can go wrong or be manipulated, showing that perception is an active process of creation rather than passive reception. Light's influence on consciousness extends beyond vision to circadian rhythms, the biological clocks that regulate sleep, wakefulness, and many other physiological processes. Specialized cells in the retina, different from those used for vision, detect light levels and send signals to the suprachiasmatic nucleus in the brain, which acts as the master circadian clock. This system synchronizes internal biological rhythms with the day-night cycle, ensuring that physiological processes occur at appropriate times. Exposure to light, particularly blue light, suppresses the production of melatonin, a hormone that promotes sleep. This is why bright light in the evening can disrupt sleep patterns and why dim, warm light is recommended before bedtime. The invention of artificial lighting has extended the day, allowing human activity to continue after sunset, but it has also disrupted natural circadian rhythms, with consequences for health and well-being. Light therapy, the controlled exposure to specific wavelengths and intensities of light, is used to treat conditions like seasonal affective disorder, where reduced daylight in winter months can cause depression. The therapeutic effects suggest that light's influence on consciousness and mood is not just psychological but has a biological basis, affecting neurotransmitter levels and hormonal regulation. The question of whether light exists without observation touches on one of the deepest questions in physics and philosophy. In quantum mechanics, the act of measurement affects the system being measured, raising questions about the role of the observer. Does a photon exist in a definite state before it's detected, or does observation somehow create that state? The Copenhagen interpretation of quantum mechanics suggests that quantum systems exist in superpositions of states until measured, at which point they collapse into definite states. This interpretation gives observation a special role, though it's important to note that observation here means interaction with a measuring device, not necessarily conscious awareness. Other interpretations, like the many worlds interpretation or pilot wave theory, offer different perspectives on this question, but all acknowledge that measurement and interaction are fundamental to quantum mechanics. Light, as a quantum phenomenon, is caught up in these deep questions about the nature of reality and observation. The philosophical implications extend to questions about the relationship between the physical and mental worlds. Light is a physical phenomenon described by equations and measurable with instruments. But the experience of seeing, of color, of visual perception, is a mental phenomenon, an aspect of consciousness. How do these two relate? This is the hard problem of consciousness, and light sits at its intersection. Some have suggested that light, or more broadly electromagnetic fields, might play a role in consciousness itself, perhaps through quantum effects in the brain or through the way neural activity creates electromagnetic fields. These ideas are speculative and controversial, but they highlight the deep connections between light, matter, and the phenomenon of awareness. The meditative quality of contemplating light has been recognized across cultures and traditions. Staring at a candle flame, watching sunlight filter through leaves, observing the play of light and water, these activities can induce states of calm and focused awareness. There's something about light that draws attention and yet allows the mind to settle, making it a natural object for meditation. This quality might stem from light's fundamental nature. Light is always in motion, never at rest, yet it can create patterns of stability and beauty. It connects the observer to distant objects and times, expanding awareness beyond the immediate present. It is both wave and particle, both energy and information, existing in a state that transcends simple categories. As you prepare to rest, consider light's role in your own consciousness. The light that entered your eyes today carried information that shaped your thoughts and perceptions. The light that will be absent when you close your eyes will allow different states of awareness to emerge. Light and darkness, vision and its absence, are partners in the dance of consciousness, each enabling different modes of experience and understanding. The relationship between light and consciousness reminds us that we are not separate observers of the universe, but participants in it. The light that enables our vision is the same light that fills the cosmos, connecting us to stars and galaxies, to the past and the future. In seeing, we are seen. In observing light, we become part of the cosmic web of information and energy that light weaves through space and time. The evolution of vision reveals the deep connection between light and life. The earliest light-sensitive cells, simple photoreceptors, appeared hundreds of millions of years ago, allowing organisms to detect the presence of light and dark. Over time, these cells evolved into complex eyes capable of forming images, detecting color, and perceiving motion. The camera eye, found in vertebrates and cephalopods, and the compound eye, found in insects and crustaceans, represent different solutions to the problem of converting light into neural signals. The diversity of visual systems across species shows how light shapes perception in different ways. Some animals can see polarized light, which helps them navigate using patterns in the sky. Others can see ultraviolet or infrared light, expanding their perceptual world beyond human capabilities. The mantis shrimp has perhaps the most complex visual system known, with 12 types of color receptors compared to humans' 3, allowing it to perceive colors we cannot even imagine. Light's influence on consciousness extends beyond vision to mood, cognition, and behavior. Seasonal affective disorder, a form of depression that occurs during winter months, is thought to be caused by reduced exposure to daylight. Light therapy, involving exposure to bright light, particularly in the morning, can alleviate symptoms by resetting circadian rhythms and affecting neurotransmitter levels. The discovery of intrinsically photosensitive retinal ganglion cells, which are not involved in vision but regulate circadian rhythms, shows that light affects the brain through multiple pathways. The relationship between light and sleep is particularly profound. Exposure to blue light, which is abundant in daylight and electronic screens, suppresses melatonin production and can delay sleep onset. This is why experts recommend avoiding screens before bedtime and using warm, dim lighting in the evening. The invention of artificial lighting has fundamentally altered human sleep patterns, extending wakefulness into the night but potentially disrupting natural circadian rhythms with consequences for health. Light's role in consciousness also raises philosophical questions about the nature of perception and reality. The fact that color is a construction of the brain, not a property of light itself, suggests that our experience of the world is not a direct reflection of external reality but an interpretation. The way optical illusions can fool the visual system shows that perception is an active process of construction, not passive reception. This raises questions about what reality truly is and how much of our experience is created by our minds rather than directly perceived. The meditative and contemplative aspects of light have been recognized across cultures. Many religious and spiritual traditions use light as a symbol of enlightenment, awareness, or divine presence. The practice of focusing on a candle flame or watching sunlight can induce states of calm and focused attention. There's something about light that draws the mind while also allowing it to settle, making it a natural object for meditation and contemplation. As you prepare to rest, consider how light has shaped your consciousness today. Every photon that entered your eyes carried information that influenced your thoughts, perceptions, and experiences. The colors you saw, the shapes you recognized, the depth you perceived, all were constructions created by light interacting with your visual system. Even now, as you read these words, light is creating the experience of text, of meaning, of understanding. Light is not just a physical phenomenon but a bridge between the external world and your inner experience, a fundamental component of consciousness itself. Despite centuries of study and remarkable advances in understanding, light retains deep mysteries that continue to challenge physicists and philosophers. These unanswered questions probe the most fundamental aspects of reality, touching on the nature of space, time, matter, and the laws that govern the universe. One of the most basic questions is, what is a photon, really? We can describe photons mathematically, predict their behavior with extraordinary precision, and use them in countless applications. But what is the ontological nature of a photon? Is it a particle, a wave, a field excitation, or something that transcends these categories? The mathematical description is clear, but the intuitive understanding remains elusive. The wave-particle duality, while well established experimentally, raises questions about the nature of reality itself. How can something be both a spread-out wave and a localized particle? The mathematical framework of quantum mechanics provides a consistent description, but the physical interpretation remains a subject of debate. Different interpretations of quantum mechanics offer different perspectives, but none provide a completely satisfying intuitive picture. The speed of light is constant and represents the maximum speed of information transfer, but why does it have the specific value it does? The speed of light appears in many fundamental equations, from Maxwell's equations to Einstein's mass-energy equivalence, but its particular numerical value seems arbitrary. Some theories suggest it might have been different in the early universe or might vary in different regions of space, but no evidence for such variation has been found. The relationship between light and the structure of space-time is profound, but not fully understood. In general relativity, light follows geodesics, the straightest possible paths encode space-time. But at the quantum level, space-time itself may be quantized, raising questions about how light propagates through a discrete rather than continuous space. Theories of quantum gravity attempt to reconcile general relativity with quantum mechanics, but a complete theory remains elusive. The nature of the quantum vacuum and its relationship to light is another area of mystery. The vacuum is not empty, but filled with zero-point energy and virtual particles. These fluctuations affect light, contributing to effects like the Casimir force and the Lamb shift. But the total zero-point energy, when calculated, gives an absurdly large value that would curve space-time dramatically, in conflict with observations. This cosmological constant problem remains one of the greatest puzzles in physics. The arrow of time, the fact that time seems to flow in one direction, may be connected to light and the initial conditions of the universe. The universe began in a low entropy state, and the increase in entropy over time creates the arrow we experience. Light, carrying information and energy, is part of this process. But why did the universe begin in such a special state? This question connects to the nature of time itself and whether it has a fundamental direction or is merely an emergent property. The measurement problem in quantum mechanics, the question of when and how quantum superpositions collapse into definite states, involves light in fundamental ways. Most measurements involve detecting photons or using light to probe systems. Does light play a special role in the transition from quantum to classical behavior? Or is it just one of many ways that quantum systems interact with their environment? The relationship between light and information raises questions about the nature of information itself. Light can carry classical information as in optical communication, and quantum information as in quantum cryptography. But is information a fundamental aspect of reality, or is it just a useful way of describing physical systems? The connection between information theory and physics, particularly thermodynamics and quantum mechanics, suggests that information might be more fundamental than previously thought. The origin of the electromagnetic field and its quantization is another deep question. Why do electric and magnetic fields exist? Why are they unified into a single electromagnetic field? Why does this field have the properties it does? These questions connect to the broader question of why the universe has the fundamental forces and particles it does, a question that may have no answer or may point to deeper levels of structure. The role of light in the early universe, particularly during and before recombination, involves processes that are not fully understood. The exact mechanism of recombination, the nature of the initial fluctuations that became cosmic structure, and the relationship between inflation and the hot Big Bang all involve light in fundamental ways but contain elements that remain mysterious. As you contemplate these mysteries, remember that the existence of unanswered questions is not a failure of science but a sign of its depth. Each mystery represents a frontier of knowledge, a place where current understanding reaches its limits and new insights may emerge. Light, as both a well-understood phenomenon and a source of deep puzzles, embodies this dual nature of scientific knowledge. The quiet secret that light holds may be that complete understanding is always just beyond reach, that each answer reveals new questions, and that the mystery itself is part of light's nature. In this sense, light is not just a physical phenomenon to be understood, but a gateway to deeper contemplation, a reminder that the universe is far stranger and more wonderful than our current models can capture. The measurement problem in quantum mechanics connects directly to light and observation. When does a quantum system transition from a superposition of states to a definite state? Most measurements involve detecting photons or using light to probe systems. The process of measurement seems to require interaction, but where exactly does the transition occur? Does it happen when the photon interacts with matter, when it's detected by an instrument, or when a conscious observer becomes aware of the result? These questions touch on the deepest aspects of quantum mechanics and the nature of reality itself. The relationship between light and information theory reveals connections between physics and computation. Light can carry classical information, as in fiber optic communication, where bits are encoded as the presence or absence of photons. But light can also carry quantum information, encoded in properties like polarization or orbital angular momentum. Quantum information cannot be copied, a fundamental principle called the no-cloning theorem, which has implications for quantum communication and computing. The holographic principle, a concept from theoretical physics, suggests that all the information in a volume of space might be encoded on its boundary, like a hologram. This idea connects light, information, and the structure of space-time in profound ways. If true, it would mean that our three-dimensional experience of space might be a projection from a two-dimensional surface, with light playing a crucial role in this encoding and projection. The nature of the electromagnetic field itself raises deep questions. Why does this field exist? Why does it have the specific properties it does? Why are electric and magnetic fields unified into a single electromagnetic field? These questions connect to the broader mystery of why the universe has the fundamental forces and particles it does. Some theories suggest that these might be the only consistent possibilities, while others propose that different universes might have different laws. The role of light in the arrow of time connects to one of the deepest mysteries in physics. Why does time seem to flow in one direction? The universe began in a low entropy state, and entropy has been increasing ever since. Light, carrying information and energy, is part of this process. But why did the universe begin in such a special state? This question connects to the nature of time itself and whether it has a fundamental direction or is merely an emergent property of physical processes. The cosmological constant problem highlights the tension between quantum mechanics and general relativity. Quantum field theory predicts that the vacuum should have enormous energy density due to zero-point fluctuations. This energy should curve space-time dramatically, yet observations show that the universe is nearly flat. The discrepancy is about 120 orders of magnitude, one of the largest in physics. This suggests that either our understanding of quantum field theory or general relativity is incomplete, or that some unknown mechanism cancels most of the vacuum energy. As you drift towards sleep, let these mysteries rest with you, not as problems to be solved immediately, but as questions that enrich your understanding, that remind you of the depth and complexity of the universe. Light will continue its endless journey, carrying information across space and time, whether you observe it or not. But in your contemplation, in your awareness of light's mysteries, you participate in the cosmic dance of observation and reality, of question and answer, of the known and the unknown. These mysteries are not failures of understanding but invitations to deeper exploration, remind us that the universe is far more complex and wonderful than our current models can capture. The journey through light's nature, from its quantum properties to its cosmic role, from its creation in stellar cores to its detection in your eyes, reveals a universe that is both comprehensible and mysterious, both familiar and strange. Light is the universe's quietest secret, not because it is hidden, but because it is so present, so ordinary, that its extraordinary nature is easy to overlook. As you prepare to close your eyes and enter the realm of sleep, where light gives way to darkness and conscious thought to dreams, remember that light will be there when you open your eyes again. It will continue its endless journey, connecting you to the cosmos, carrying messages from distant stars and galaxies, from the early universe, from the quantum vacuum itself. The photons that will greet you in the morning have been traveling. Some for 8 minutes from the sun, some for years from nearby stars, some for millions of years from distant galaxies. They carry with them the history of everything they have encountered, the information encoded in their wavelengths, their polarization, their intensity. In receiving this light, you become part of a cosmic network of information and energy that spans space and time. Light is your constant companion, even when you cannot see it. Infrared radiation warms you. Radio waves carry communication. Microwaves heat your food. X-rays reveal the structure of your bones. All of these are light, different frequencies of the same fundamental phenomenon, the same quiet secret that underlies so much of reality. As sleep approaches, let your awareness of light become gentle, soft, like the fading of daylight into twilight. There is no need to grasp or analyze. Simply rest in the knowledge that light exists, that it connects you to the universe, that it is both particle and wave, both energy and information, both ordinary and extraordinary. The universe's quietest secret is not that light is mysterious, but that it is so fundamental, so woven into the fabric of existence, that to understand light is to understand something essential about reality itself. And yet, complete understanding remains just beyond reach, not as a failure but as an invitation to continued wonder and exploration. In the darkness behind your closed eyes, light has not disappeared. It continues its journey, and when you dream, perhaps your mind will process the light it received today, creating images and experiences from the photons that entered your eyes. Even in sleep, you remain connected to light, to the cosmos, to the endless flow of information and energy that light represents. When you wake, light will be there to greet you, carrying new messages, new information, new connections to the universe. The cycle will continue as it has for billions of years, as it will for billions more. Light is eternal in its journey, even as individual photons are created and destroyed, even as the universe evolves and changes. Rest now, with the understanding that light is both known and unknown, both understood and mysterious, both ordinary and extraordinary. Let this gentle paradox lull you towards sleep, like the soft glow of a distant star, like the quiet whisper of the universe's most fundamental secret. The question, what is light, has no single, complete answer. It is a wave and a particle. It is energy and information. It is a time traveler and a reality creator. It is a quantum phenomenon and a cosmic force. It is the universe's quietest secret, present in every moment, fundamental to existence, yet always holding something back, always maintaining a mystery at its core. As consciousness fades and sleep approaches, let light be your guide into the darkness, not as something to be grasped or understood completely, but as a companion in the journey of awareness. Light has traveled far to reach you, and it will continue its journey long after your eyes close. In this continuity, in this connection across space and time, find peace. Find rest. Find the quiet secret that light offers, that you are part of something vast and beautiful, connected through photons and fields, through energy and information, to the cosmos itself. Sleep well, with light as your quiet companion, with the universe's secret held gently in awareness, not as a problem to be solved, but as a mystery to be lived. The photons will continue their endless journey. The waves will continue their oscillations. The fields will continue their fluctuations. And you, in your rest, remain part of this cosmic dance, connected through light to everything that is, everything that was, and everything that will be. The journey through light's mysteries has taken us from the quantum realm to the cosmic scale, from the birth of the universe to the present moment, from the fundamental nature of reality to the experience of consciousness. Light is all of these things and more: a wave and a particle, energy and information, a time traveler and a reality creator, a quantum phenomenon and a cosmic force. As you prepare to close your eyes, remember that light will continue its endless journey. Photons are being created in stellar cores right now, beginning journeys that will last billions of years. The cosmic microwave background continues to stream in from all directions, carrying messages from the universe's infancy. The light from distant galaxies is still traveling, still carrying information about cosmic history. And when you open your eyes in the morning, new light will greet you, connecting you once again to this vast cosmic network. Light is the universe's quietest secret, not because it is hidden, but because it is so present, so fundamental, that its extraordinary nature is easy to overlook. In every moment, light is creating your experience of reality, carrying information across space and time, connecting you to the cosmos. This connection is not metaphorical, but literal. The photons reaching you are the same photons that have traveled from stars and galaxies, from the early universe, from the quantum vacuum itself. The question, what is light, has no single, complete answer, and perhaps that is part of its nature. Light exists at the boundary between the known and the unknown, the understood and the mysterious. Each discovery reveals new questions, each answer opens new mysteries. This is not a failure of understanding, but a sign of light's fundamental role in the structure of reality. As consciousness fades and sleep approaches, let light be your guide into the darkness. Not as something to be grasped or understood completely, but as a companion in the journey of awareness. Light has traveled far to reach you, across billions of years and billions of light years, carrying the history of the cosmos. It will continue its journey long after your eyes close, connecting moments and places across the vast expanse of space and time. In this continuity, in this connection, find peace. Find rest. Find the quiet secret that light offers, that you are part of something vast and beautiful, connected through photons and fields, through energy and information, to the cosmos itself. The universe's quietest secret is not a puzzle to be solved, but a mystery to be lived, a connection to be experienced, a reality to be embraced. Sleep well, with light as your quiet companion, with the universe's secret held gently in awareness. The photons will continue their endless journey. The waves will continue their oscillations. The fields will continue their fluctuations. And you, in your rest, remain part of this cosmic dance, connected through light to everything that is, everything that was, and everything that will be. Good night. Rest with light. Fall asleep with the universe's quietest secret.